Hello, I'm Mike McCulloch. So today I want to talk to you about the simplest way to derive quantized inertia, which is incredibly simple and elegant from information. So we first start from Landauer's principle that says that every time you erase a bit of information, you release a certain amount of energy, which is given by, well, E is kT times log to the base 2 of 2. So K being Boltzmann's constant and temperature being the temperature, T being the temperature. It turns out that if you do a little bit of maths, that the energy you get from deleting n bits of information is kT times n, ktn. So that's nice and simple. So now I'm going to consider an object which is shown here as the vertical dashed black line shown on this diagram, which should be up here somewhere. So this is an object, so it's imagine it as a long rod, if you like, split up into Planck lengths shown by the dashed lines. Now, before it accelerates, this object can see all the way out to the cosmic diameter, which is shown by the red vertical line on the right. So it can see a certain amount of length. So I've shown that with the dots extending from the left to the right, and each of those dots represents a Planck length. And what I'm assuming is that each Planck length contains one bit of information, and that makes sense because a Planck length is the smallest distance you can store information in. Okay, so now the object on the left accelerates to the left, so it will now see a Rindler horizon, so an acceleration horizon, which is shown by the blue vertical line in the center. So now it won't see as many bits. A lot of bits will have been erased. They'll be behind the horizon. So this means that it looks like the entropy has gone down, but that can't be right because nature doesn't allow that. So we have to allow some energy to come out. So what is that energy? Well, the energy is going to be the difference between the kT times number of Planck lengths we had minus kT times number of Planck lengths we now have. So it's a difference in those two things. And you can write this down. So the number of bits that we had is the distance to the cosmic horizon, which is theta over 2 divided by the Planck length. And the number of bits we have after acceleration is given by the distance to the Rindler horizon, which is c squared over a divided by the Planck length again. And if you take the difference of those, you get a certain formula which is shown here. And then if you use equals mc squared to replace the energy with the mass, you assume also that the energy is thermalized, so E equals kT. And if you do that, then you get an equation which starts to look like the quantized inertia equation. So, and that's shown here. So the only thing we need to do now is accept the fact that we had a vertical extended rod, and we just need the inertial mass for one bit of it. So we divide by the length of the rod, which is the theta over 2 LP, the cosmic radius divided by the Planck length, and you get this formula, which is the formula for quantized inertia, which gives us the energy available for inertial mass. And you see it's not quite a simple formula, and the difference, so the second term in the equation is the term that enables us to predict galaxy rotation and all these different anomalies with quantized inertia without the use of dark matter or anything like that. So this is a very nice derivation that I published in 2020 in a paper. I made a bit of a mathematical error in that one, but the result was still valid, and I published it in correct form in my book, which is shown here. So feel free to read that. and after this video is over, I'll put a screenshot of the full calculation so you can have a look at it. Okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.